how Newton might interpret gravity was adequate to permit us to fly from the Earth to the Moon at any point. Get yourself lost in the ticking hands of time, contemplating whether how we might interpret it is simply the tip of the worldly ice shelf on its head. His disclosure isn't simply a hypothesis. A key could open the ways to the secrets of the universe, uncovering a universe more perplexing and motivating than we at any point thought for a second to imagine. How does Brian Cox's new hypothesis challenge our customary understanding of time? And what are the potential suggestions for our view of reality? Join us on a charming investigation through the chronicles of time itself as we dive into Brian Cox's, as of late, uncovered momentous hypothesis on the concept of time in the huge universe around us. Secrets are waiting to be uncovered, and a portion of these secrets involve confounding things about time and gravity, which are fundamental portions of our reality. Imagine a world where time acts oddly. It can, by the same token, dial back or accelerate. Likewise, the power that keeps us on the ground probably won't be what it seems. This is the domain of Albert Einstein's theories of relativity, where how we might interpret time and gravity veers off in an unexpected direction. Albert Einstein, a notable name, gave us a better approach for taking a gander at the universe through his theories of relativity. His work established the groundwork for understanding how time acts in various circumstances, particularly when going at very high rates. It all started in the mid-20th century when Einstein proposed two momentous theories, the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we might interpret reality. In basic terms, it lets us know that the laws of physics remain the same for all observers who aren't accelerating, no matter what their motion. This hypothesis presents the possibility of relativistic effects, including the renowned thought that time can widen or dial back under certain circumstances. One interesting psychological test used to make sense of time dilation is the light clock. Imagine being inside a spaceship moving extraordinarily fast, nearly at the speed of light. Inside the spaceship, there's a light beam skipping between two mirrors, opposite to the course of movement. As per the laws of physics, the speed of light is steady for all eyewitnesses. So, the light beam must seem to go along a more extended, corner-to-corner way. The time it takes for the light beam to travel its way ought to be the same for both the observer inside the spaceship and the one outside. Anyway, since the way is longer for the outside observer, it seems like it would take additional time for the light to finish its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the fixed observer. In this situation, time acts in an unexpected way, contingent upon your movement. Getting at how things change when they move fast, known as relativistic effects, isn't simply a hypothetical thought. Researchers use enormous machines called particle accelerators, like the Large Hadron Collider, to make particles go really fast, nearly as fast as light. When things move this quickly, we need to ponder time in an exceptional method for making precise forecasts and estimations. Albert Einstein thought of the special theory of relativity in 1905, and it changed how we see the universe, particularly when it comes to time and movement. This hypothesis challenges what we might normally think. It says that the standard rules of physics are no different for everybody, regardless of whether they're moving. This is different from our ordinary experience, where we could imagine that if something is already moving and we add more speed, it gets quicker. However, Einstein's hypothesis says there's a maximum speed that nothing can go faster than, and that is the speed of light. In this perspective, events that seem to occur simultaneously for us probably won't appear to be that way for people moving around nearly as fast as light. Another idea that comes from this unique perspective is length contraction. This means that if something is moving, it looks more limited in the direction it's moving when seen from a fixed spot. Then, there's the well-known equation E equals mc squared, which demonstrates how energy and mass can transform into one another. This is crucial for understanding how minuscule particles act while they're zipping around super fast, and also for things like what happens when atoms split in nuclear reactions in the real world. Special relativity isn't simply an extravagant hypothesis. It's something we use in everyday advances, like GPS. When GPS satellites send messages to your device, they're moving. And because of this movement, time acts a little differently for them. If we didn't consider this time dilation effect in our GPS calculations, your navigation would be misguided. So, special relativity teaches us that time isn't the same for everything and everyone. It depends on how things are moving. This idea challenges our thought process about existence. It's like saying our ordinary understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed, it's impacted by movement. Some basic ideas, like the speed of light always remaining the same and how energy and mass are connected, have been proven by various experiments. Yet, there's more. Enter Albert Einstein's general theory of relativity from 1915. This hypothesis digs deep into the connection between gravity and how the universe is organized. It turns the old idea that gravity is only a force that pulls things from a distance on its head. Instead, it tells us that gravity occurs because space-time is bent or warped. It's like saying, hey, gravity isn't a baffling force, it's just how things naturally move in the universe. According to Brian's understanding, general relativity means thinking of the universe as a four-dimensional substance, combining 3 dimensions of space and 1 of time. In this framework, massive things like stars, planets, and even us influence how reality is shaped around us. This warping creates gravity. Imagine space-time like a big, stretchy blanket. When something heavy like Earth is placed on it, it makes a dent in the blanket. If you place something smaller like a ball near Earth, it will move toward the dent. This is like the way objects act because of gravity, not some puzzling force, but rather a response to the bending of space-time. General relativity gives a strong explanation for how things move in our solar system. For example, planets orbiting the Sun. It can precisely tell us the paths these planets take, including how Earth follows an oval-shaped circle around the Sun. According to Brian, this is different from the old idea of gravity simply arranging things, which struggled to explain how planets move as they do. The novel idea is that space-time is bent like a bendy fabric, which fits better with what we observe. A significant moment that confirmed the correctness of general relativity happened during a solar eclipse in 1919. Sir Arthur Eddington led a team to see how light from faraway stars bent as it passed near the Sun. According to the theory, the Sun's mass would cause the starlight to bend slightly during the eclipse. The observations matched Einstein's predictions, proving the validity. Especially impressive, time moves more gradually, contrasted with regions with more vulnerable gravity. So, in the event that you were standing near a monstrous item, like a dark opening, your clock would tick more leisurely than one set far away from this strong mass. General relativity presents the thought of dark openings, which are districts where gravity is really extreme. Inside a dark opening, the gravitational power is so strong that nothing, not even light, would be able to escape from it. The edge encompassing a dark opening is known as the occasion skyline. Furthermore, it resembles a final turning point. Once something crosses this limit, it gets maneuvered into the dark opening with practically no chance of returning. Einstein's hypothesis of general relativity has critical suggestions for how the universe is organized. At first, he added something called a cosmological steady to his conditions, since he thought the universe was static. Anyway, when we found it is extending, he alluded to this as a serious mix-up. The thought of an extending universe, in view of general relativity, is a critical piece of the huge explosion hypothesis, which makes sense of how the universe started. One more significant idea from general relativity is gravitational waves. These are swells in the texture of reality brought about by exceptionally monstrous objects moving quickly, like when dark openings or neutron stars converge. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory straightforwardly identified gravitational waves, giving confirmation to one more part of Einstein's hypothesis. Over time, researchers have led various tests to confirm whether general relativity is valid, and each time it has shown to be right, whether by seeing how planets move, the twisting of starlight, or the discovery of gravitational waves. While saying gravity is completely false may amaze, particularly since we all experience gravity each day, in the realm of physical science, it's not unexpected to examine and investigate various thoughts. Researchers, like Brian, frequently question laid-out hypotheses, and in the domain of gravity, some test the ordinary way we ponder this key force. One thought that difficulties conventional gravity is called adjusted Newtonian elements, M, which suggests that gravity acts diversely at slow rates, especially in cosmic systems, without the need for dull matter. As opposed to adding imperceptible matter, M suggests that gravity reinforces at low velocities. The gravity banter additionally includes the baffling ideas of dull matter and dim energy, introduced to make sense of specific peculiarities in space. Pundits contend that these aren't essential and that elective thoughts would be able to represent what we notice. Some researchers who can't help contradicting Einstein's gravity hypothesis investigate additional opportunities, for example, speculations including obscure particles or powers that could change or upgrade how we might interpret gravity. It's vital to accentuate that, in science, novel thoughts are not ignored. Rather, they are thoroughly tried to check whether they appear to be legit. For model, Einstein's thought about time in four-dimensional space, where time travel may be restricted by the speed of light, has been inventively considered, close by thoughts like wormholes and alternate ways. Stephen Hawking's sequence protection guess proposes that traveling once more into the past seems far-fetched from a physical science point of view. Progressing examinations and perceptions try to decide if these new hypotheses can make sense of peculiarities like the power of gravity in a way steady with what we definitely know. While different thoughts have been examined, none have persuadedly supplanted the notable rules of gravity. Questioning and testing are fundamental to challenge laid-out thoughts, and they are part of how science advances, prompting further exploration and a more profound comprehension of the universe. In the domain of gravity hypotheses, general relativity remains the most significant and effective one. In spite of challenges and elective thoughts, it reliably performs well in tests and makes sense of different peculiarities, like how planets move and how light curves around huge objects. General relativity remains solid since it is basic and includes many peculiarities. As recently talked about, Einstein's extraordinary hypothesis of relativity suggests that time can act contrastingly founded on how you're moving. Now, how about we investigate how this thought influences genuine situations, particularly in space travel? Space travel is energizing, be that as it may, testing, since space is huge. Furthermore, as per Einstein's hypothesis, the speed of light is the quickest anything can go. This makes going between stars a huge test, even with cutting-edge innovation, due to the extensive time it takes to arrive at the nearest stars. Consider the well-known twin conundrum. To comprehend what occurs with time when you travel in space, picture this. One twin stays on Earth while the other twin goes on a quick outing to a far-off star. At the point when the space-voyaging twin returns, they figure out that less opportunity has passed for them than for their twin on Earth. This implies they have successfully voyaged into the future. Time is pivotal for space explorers, in light of the fact that the longer the venture, the additional time dials back. If space travelers were to visit close-by stars, where time dials back essentially, they could progress in years more leisurely than individuals on Earth. While this might seem like a sci-fi story, it's a certifiable impact from the hypothesis of relativity. Envision if people sent a team to a star framework not excessively far away. Due to the colossal distance, the outing could take numerous years. Regardless of whether they travel quick, for the space travelers on the spaceship, time would feel more limited as a result of the time enlargement impact. Yet, on Earth, a lot of time would have passed. Time expansion influences living creatures as well as innovation. PCs and correspondence gadgets on rocket should represent time expansion for precision and appropriate working. Space travel at high velocities presents actual difficulties, for example, drawn-out disengagement and openness to vast radiation, as well as the mental impacts of being away from Earth for a lengthy period. In our regular routines, we can notice the impacts of time enlargement in the worldwide situating framework. GPS depends on the exact timing of signs from moving satellites. Since these satellites experience time expansion, it is pivotal to figure these impacts for exact GPS estimations. Neglecting to do so would essentially influence the accuracy of route frameworks. Currently, how about we investigate why time moves in a single course? Time oversees our lives in the universe, moving from the past to the present and into the future. This one-way excursion of time is essential to our reality, but why does time have this one-way nature? To comprehend, we check out at entropy, an idea that measures disorder or arbitrariness in a framework. Entropy, connected to the bolt of time, will in general increment over the long run, causing time to stream in one course. The second law of thermodynamics expresses this relationship, stating that in any disengaged framework, total entropy will either increment or, best-case scenario, remain steady. In basic terms, entropy normally will in general develop and doesn't decline on its own. Seeing how things end up being more cluttered around us helps us see the one-way progression of time. Envision a deck of cards, generally conveniently organized. If we mix them, they become untidy and irregular. This change from request to jumble outlines how time moves in one course, as seen in ordinary peculiarities like ice softening or a mixed mug of espresso becoming turbulent.